Hello, in this lecture we are going to discuss common emitter configuration and common collector configuration of BJT transistors. So, common emitter configuration, this is the most frequently used configuration. Same thing which we discussed earlier, that in active region base emitter junction should be forward bias and base collector junction should be reverse bias. In this case we can see a common emitter configuration is represented in these two figures. One is for NPN and other is for PNP transistor. In this case, you can see that emitter is at common or at ground potential with reference to input and output. In other words, we can say that we apply input at base emitter junction and we measure output at collector to emitter junction. Here we can see in the form of symbols. You can see for NPN transistor the IB and IC both are coming inward to the transistor and IE is leaving from transistor. This is for NPN, that is not pointing in, and for PNP the current directions are opposite, that IC and IB both are leaving out and IE is uh, coming into the transistor. And we need two sets of characteristics. One is for input characteristics and the other one is output characteristics. For input characteristics, we plot characteristic curve against input quantities, that is VBE at x-axis and IB at y-axis. In this case, you can see that IB is the input current and VBE will be the input voltage. And there are three curves. These are against different VCE, that is collector to emitter voltage. And if we remember the forward bias condition of diode or a PN junction, the curves are similar to that one, that is a forward bias diode. And if you consider the material as silicon material, then the knee voltage is around 0.7 volt. And for the output characteristics, these are the plot of output characteristic curves. We plot output characteristic curves against VCE and IC. VCE will be the output voltage and IC, the current, is the output current. And each curve is against a fixed value of input current, that is IB. For IB is equal to 0 microampere, we have this curve. For IB is equal to 10 microampere, we have this curve. And for IB 20, 30, 40, we have these different curves. One thing you must notice, that when IB or the input current is 0, in this case IC is not equal to 0. We will explain this in greater detail why IC is not equal to 0 when the input current IB is equal to 0. So to explain this, we consider this equation, which is, you can say, is universal for BJTs, that IE is equal to IC plus IB. That is, emitter current is equal to collector plus base current. And this equation we already have discussed earlier, that IC have two components. One is IC majority and the other one is IC minority, which we call ICO or ICBO. And when we have defined alpha, we defined alpha as amplification factor of majority carriers. So if we write IC majority in terms of alpha, then we know IC is equal to alpha IE. Here IC we mention here is the IC majority. So IC is equal to IC majority plus IC minority. We can rewrite this equation as IC is equal to alpha IE plus ICBO. Now putting IE from this equation to this equation, we will have this equation that says IC is equal to alpha IC plus IB plus ICBO. And with little math and rearranging, we will get this equation, that is IC is equal to alpha IB over 1 minus alpha plus ICBO over 1 minus alpha. You can easily get this by multiplying alpha to IC and bringing it over this side, and then taking IC as common, you will have 1 minus alpha, and then you can divide on other side. So now we have this equation which says IC is equal to alpha IB over 1 minus alpha plus ICBO over 1 minus alpha. This ICBO is actually due to minority carriers, and in case of diode it was stated as reverse saturation current. So if we consider the IB is equal to 0 in this equation, then and put a typical value of alpha in this equation, which is 0.996, the resulting collector current IC will be IC can be calculated here. Putting IB is equal to 0 and putting alpha is equal to 0.996, this part will be 0, and then ICBO over 1 minus 0.996, that will be 0.004, this will be equal to 250 ICBO. Now going back to the graph, if we have IB is equal to 0, we will have 250 time reverse saturation current. 250 time reverse saturation current. So in this case, if you have a very small value of ICBO, that will be amplified by 250 times, so that will become IC for IB is equal to 0. That is why for IB equal to 0, we have a notable value of IC which we cannot ignore anymore. So for the least distortion amplification purposes, we will have a cutoff region beyond this, where IB is equal to 0 and IC is equal to ICEO, which is majority, which is actually the amplified minority carrier flow. And we can define this ICEO with this, which says that uh, collector to emitter current when base terminal is open. When base terminal is open, automatically IB will be equal to 0. And it states that ICEO collector to emitter current when base is over open. We have shown graph here. Now if we want to approximate this curve, these three curves to a single curve, you can get approximation with this straight line which actually ignore the resistance and which actually ignore this knee value. So you can easily derive the relation that VBE equal to 0.7 volt. Solving this example, in this first question is using the characteristic of given figure, determine IC at IB is equal to 30 microampere and VCE is equal to 10 volt. So in this case, when IB is equal to 30 microampere, we are on this curve. For IB is equal to 30 microampere and VCE is equal to 10 volt. VCE is equal to 10 volt. We are on this line. This is actually this point. We have to find IC. So by graph we can find IC here, which is 3.4 milliampere. Now second question is using characteristics of given figures, determine IC at VBE is equal to 0.7 volt and VCE is equal to 15 volt. Now VBE is equal to 0.7 is here at input characteristics. So at 0.7 IB is approximately equal to IB in this case is approximately equal to 20 microampere. So for 20 microampere we are at this characteristic curve, and for VCE is equal to 15 volt. VCE is equal to 15 volt. This point, this point, we can find IC by simply drawing a straight line here, and the intersection of this axis is at around 2.5 milliampere. If you draw a straight line, then this will be around 2.5 milliampere. So in other words, we can find these quantities through these characteristic curves. Now we have to define a beta, which is common emitter forward current amplification factor. In this case, for common emitter configuration, we have input current IB is the input current and IC is the output current. So relation of these two is actually beta. So beta DC DC means when we have fixed, we are just applying DC voltages, or we, in other sense, we are just biasing the transistor, we will have beta DC. In this case, IC and IB will be fixed for some certain fixed values of voltages applied. So beta DC is defined as IC over IB, or you can say it relates the level of IC to IB. In AC mode, when we apply AC signal on top of this DC biasing, then the current level of IC will also fluctuate, as well as IB will also fluctuate. For that case, we can define beta AC as change in IC over change in IB. That is delta IC over delta IB for certain fixed VCE. In this graph, it is shown how we can find beta AC. In this case, if we fix VCE at 7.5 volt, and we had IB is equal to 25 microampere. So in this case, applying an AC signal will shift this Q point upward and downward. That is, IB will move upward and downward in this graph. In this case, we consider that IB will move 5 units upward and 5 units downward. That is, now IB is 30 microampere for positive peak and 20 microampere for negative peak. So again, we have shown this graph here. Now we have to find beta AC. So beta AC can be defined as change in IC over change in IB for certain fixed value of VCE. So change, you can represent it here like IC2, delta IC is equal to IC2 minus IC1, and delta IB can be written as IB2 minus IB1. So as we said, for fluctuation we consider is that IB2 is 30 microampere and IB1 is 20 microampere, and for corresponding values of IC, which you can find by drawing a straight line over here, you can find value of IC2 against IB2, and you can find value of IC1 against IB1. That will be 3.2 milliampere, and IC1 is 2.2 milliampere. So the change is 1 milliampere, change in IC actually, and change in IB is 10 microampere. So calculating this, we will find beta AC equal to 100. There is no unit because this is ratio. Now at the value of IB is equal to 25 microampere, we have beta AC equal to 100. We can find beta DC here by putting the value of IB 25 microampere and corresponding value of IC, which is 2.7 milliampere, and we will get beta DC equal to 108. One thing we must note that beta AC and beta DC, both values are almost similar, and most of the time we will be using these values interchangeably. You have beta AC or beta DC, you can use it in the equation. This is another example where we have approximated uh, the curves with the straight lines which are not actually the straight lines. This is due to output impedance. So if we ignore that, you consider output impedance infinite, we will have these straight lines. And again, if you ignore VCE saturation, you will consider it as 0. We will get this graph. And for this, if you want to find beta AC and beta DC, both values will be equal. Now we can find a relationship of alpha to beta. We know beta is equal to IC over IB, and IB is equal to IC over beta. And we also know that alpha is equal to IC over IE, and IE is equal to IC by alpha. Substituting to these values to this universal equation, we will get, instead of IE, you write IC over alpha, and instead of IB, we write IC over beta. So in this equation, we have IC only current value, that is IC. So you can find uh, relation of alpha to beta like this. 1 over alpha is equal to 1 plus 1 over beta. That is dividing both sides of equation with IC. Rearranging this equation will give you beta is equal to alpha beta plus alpha, and you can write this as beta plus 1 into alpha. So we can derive this equation, this relation actually, like alpha is equal to beta over beta plus 1, and beta is equal to alpha over 1 minus alpha. The explanation of this relation is given here. This is also similar. You just need to write beta in terms of alpha. Now this part will give us relation of ICBO to ICEO. Since we know that ICEO is equal to ICBO over 1 minus alpha, and we also know that 1 over 1 minus alpha is equal to beta plus 1. So putting this thing into this equation will give us ICO is equal to beta plus 1 into ICBO, and in this case, since the value of beta is around 40 to 400, 40 to 400, so beta plus 1 can be approximated with beta. So with this approximation, that is beta plus 1 is equal to beta, we will get this equation ICO is approximately equal to beta ICBO. Now this slide will show how we actually bias the transistor. In case of common emitter configuration, we need to bias this with two voltage sources. What source you need to connect here and here, that that actually establish the flow in these defined directions. So we have to connect VBB in this polarity and VCC in this polarity to actually establish current in this defined direction. The third configuration is common collector configuration, where collector is at common or at ground potential with reference to input and output. So in this case, PNP transistor, and for NPN transistor, so biasing is shown here. We apply input at base collector junction and we measure output in this part, which is collector emitter. And using symbols and current direction, these figures actually show the direction of currents. Common collector configuration is generally used as impedance matching, since the input impedance is quite high for this case. Now, since we need to define some linear region of operation of a transistor, so that we get an undistorted output signal and undistorted amplified output signal, so we should have a defined region of operation. For that, we need to define some limits of operation. Limits will tell us where we need to bias our transistor so that we can get undistorted output signal. In this case, we have uh, certain limitation on IC and VCE, and also their product, that is power dissipated by this transistor. In this case, the first inequality define that IC should be less than equal to IC max and greater than equal to ICEO. On the graph, if we want to see that this is the point, that is 50 milliampere is IC max point. So IC, or the output current, should be less than 50 milliampere and should be greater than ICEO, which will have certain value. So IC should be in this range. And limits on VCE is defined through this inequality that tell us that VCE should be less than equal to VCE max and should be greater than or equal to VCE saturation. Here VCE saturation is defined and VCE max is defined as 20 volt. So the VCE should be in this range, that is VCE saturation to VCE max, in this case 0.3 volt to 20 volt. And the limitation on power curve should be that VCE IC, it is actually power dissipated by the transistor, should be less than PC max curve. This curve is for PC max. Let's say PC max is, in this case, is 300 milliwatt. So the product of these two values, that is VCE and IC, should be less than 300 milliwatt at any region. And this is the PC max curve, which define the maximum power dissipated by the transistor, should be less than this one. So we need to bias transistor somewhere in this region depending upon application to get undistorted output signal. That is the end of this lecture.